Thank you very much for coming. Unfortunately, Tiancheng couldn't come to Boston himself, so I'll be the one delivering the talk today. As we all know, the training compute requirements have been growing exponentially over the recent years to train the frontier large language models, specifically 4 to 5x increase per year. And this means that if we want to catch up with this trend, we need to scale both up and scale out our training infrastructure, which in fact increases the power demands. Even though the industry leaders have been trying to tackle this issue by securing stable sources of power, eventually we will come to a local power limitation problem. One of the solutions would be to try and train across multiple data centers. And in fact, the industry leaders such as Google, Microsoft, and also OpenAI have been looking into this problem for quite some time now. And we have one quote from the CEO of Google Cloud. Even though they don't disclose the exact details, they confirm that the Gemini Ultra was already trained across multiple sites and even across multiple clusters within those sites. So in our paper, we are trying to address the question, how do we do the cross-data center training efficiently, and especially with the open source stack? The main challenge in our setting is that on the cross-data center boundary, we have a much higher latency and lower bandwidth. And I will present two concrete examples. One is that we have cross-campus clusters. Typically, this uses specialized and expensive interconnects, so we can keep the high bandwidth. However, we cannot fight the physical distance, so we will incur a higher latency in this setting. The other case could be cross-region cloud, where we use typically more commodity level and cheaper interconnects, so we have even lower bandwidth and incur higher latency than in the cross-campus clusters. How do we split the actual LLM training is by using several hybrid parallelism techniques, such as the tensor parallelism, sequence parallelism, also sometimes called context parallelism, expert parallelism for the mixture of expert models, pipeline parallelism, and data parallelism. For the cross-data center boundary, the first three are not very suitable because they incur much higher frequency and volume, communication volume. So we are left with two feasible options, which is the pipeline parallelism and the data parallelism. On the left, you can see a typical large language model with the first embedding layer, then multiple transformer blocks, and finally the output projection. And you can see how we can split such model in the cross-data center setting for the data parallelism case and for the pipeline parallelism case. Now, in terms of communication, for the data parallelism, we need to synchronize the gradients. So we need to do all reduce or reduce scatter and all gather collectives across the data center boundary. And in the pipeline parallelism, we need the point-to-point communication to communicate the activations in the forward pass and the gradients in the backward pass. We will revisit the question, which one of these two is better, but I will start with looking into the possible cross-data center parallelism setting. We will start with the true or so-called data dependencies in the pipeline parallelism setting. We'll dive a little bit deeper into the transformer block, and we see that this is just a linear layers with the forward path and the backward path, and we have a data dependency such that the forward block must come before the backward block. In terms of actually splitting the model, we can chunk the model in several ways, and then use some kind of traversal patterns to move the data across several devices, or sort of split the model across several devices. One of the most basic one is this unidirectional traversal pattern. But what we can do is to chunk the model further into finer grained blocks and introduce two more traversal patterns, specifically the loop one and the wave traversal pattern. This gives us much finer granularity. Of course, the trade-off is that now we need to do a little bit more communication. What prior work has shown to us is also that we can split the backward block onto the separate data gradient computation and the weight gradient computation. We will achieve finer granularity and also a little bit more balanced blocks, because now the size of individual blocks are more or less the same. So this is sort of the scope of all of the true dependencies at various granularities that we'll use to construct our schedules. We have these data dependencies, and we also have several micro batches, and we'll feed this into our scheduling strategy. What the scheduling strategy does is that it simply orders how the blocks should be executed on individual devices. Both of these dependencies give us specific pipeline schedules, and I just listed a few of the state-of-the-art schedules, as you can see on the slide. When we will dive a little bit deeper into one of the schedules, the 1F1B schedule, in the single data center setting, you can see for 8 microbatches how it looks like. And one important point is that in the single data center setting, we usually don't consider the communication cost. So we have a high bandwidth and low latency, and we assume that the communication is more or less instant. However, in the cross-data center setting, it will become a problem because we will incur a significant latency and bandwidth delay on the cross-data center boundary. And in fact, we can visualize this, how it looks like. We insert the cross-data center boundary between the device 1 and 2, and we see that now these idle blocks or idle spaces appear in the pipeline. We call these spaces pipeline bubbles, these idle blocks. And you can also see this more regular pattern, which we call bubble strides. And this is not specific to the 1F1B schedule. As you can see, for any schedules that I listed here, when we even add more devices and we introduce the data center boundary, you can see these strides very clearly. And the question is, what can we do about these bubble strides? One of our approach is to constructing optimal schedules, so framing this as a job scheduling problem. But additionally, we will model specifically the communication time using the alpha-beta model. The input into our job scheduling problem will be the duration of individual operations. That means the compute operations, so the individual blocks, but also now the bandwidth delay, which is on the cross-data center boundary, but also within the individual data centers. Moreover, the latency, so latency between any devices. Then we have memory changes in a single device, and also the device memory limit, and of course the data dependencies that we established before. Now, the objective is to minimize the make span of the schedule. And what we use is constraint optimization solvers to do so. By doing so, we can reorder the same pipeline as you can see on the right, which will make the bubble ratio smaller, make the whole schedule faster, and it will keep the same peak memory. However, we have one small limitation with this approach, and that's, of course, the solver runtime. To address this issue, we introduce a greedy schedule generation, and this is specifically for situations where we have a dynamic network conditions. That might be that the delay or the bandwidth delay or the latency changes on the global links or even on the local links, and we need to, on the go, basically change the pipeline. And in those cases, the solver runtime is a limitation because we need to act fast. Our greedy schedule is an algorithmic approach, and we call this sub-block scheduling. And just to illustrate how it works, we have the local view per device. We have also the set of blocks that are ready to be scheduled. We further split those blocks into several sub-blocks, and then we can basically schedule these sub-blocks with some kind of interleaving, which is allowed. Of course, there are some constraints to this, and in general, we follow exactly the same constraints as for the optimal schedules. So there is no additional memory or anything like that. What we see with this is that we can generate the schedules much faster. We adhere to the same constraints. And as we will see in the evaluation section, we will arrive at the near optimal schedules. So this is very attractive alternative to the optimal schedules. Now we will revisit the question if the cross-data center data parallelism is better or worse than the cross-data center pipeline parallelism. We will use a performance modeling to answer this question. And specifically, we will take a Llama 3 405 billion model. We will span this model across 2 data centers with the same parallelism dimensions as described in the Llama 3 training technical report. And I just noted down the time it takes for the forward block to finish. This will help us to sort of compare with the additional latency that we inject in the cross-data center boundary, such that we know what orders of milliseconds or time we are talking about. Now for the pipeline schedules in those settings. So for the cross-data center data parallelism, we will use the state-of-the-art zero bubble schedule such that we have a fair comparison. And for the cross-data center pipeline parallelism, we will use our optimal CrossPipe schedules, as you have seen in the slides before. And the traversal patterns that will be used is always we select the best one that achieve basically the best performance for the individual case. What we do is we vary the latency, so from 2 milliseconds to 128 milliseconds, and we also vary the bandwidth on the cross-data-center boundary from 4 gigabytes per second to around 1,000 gigabytes per second. What we will be looking at is the speed up of the cross-data-center pipeline parallelism when compared to the cross-data-center data parallelism. As you can see from the results, the cross-data-center pipeline parallelism is the better choice in every one of these scenarios, and you can see also which traversal pattern was used underneath the speed-up number. Since we established now that the pipeline parallelism is the way to go, we described briefly how do we implement the CrossPipe into the production level, state-of-the-art training framework, Megatron LM. We introduce our CrossPipe module, and as a first step, we do some lightweight system profiling. What it means is that we need to get a sense of what kind of setup we are operating in. So we will try to find out the latency and the bandwidth delay, the static memory allocation, the activation memory and runtime of the individual pipeline blocks. We feed this information into our dynamic schedule generator, where we have several traversal patterns, as I showed at the beginning, and we have also the option to split the B block into the D and W blocks. With the dynamic schedule generator, we generate optimal schedules and also the greedy schedules. As a next step, we have a selection of schedules that we can pick from. We have the dynamic ones that are fitted to the exact hardware setup that we are operating in, but we also have the static ones that are widely available to choose from, and we choose the best one. As a next step, we do execution plan generator, and what it means is that we insert the point-to-point asynchronous communication to align with the pipeline. We ensure deadlock freedom, and we also try to maximize the overlap of the communication and the computation. I'll just very briefly describe this optimization because during the development of CrossPipe, we have found out that for the cross-data-center, in the cross-data-center scenario, the original implementation of Megatron, it could sometimes happen that the receive was posted quite late. And since Nickel implements the rendezvous protocol to first synchronize the send and the receive and then do the transmission of the data, there were sometimes cases where there was additional bubbles incurring because of this phenomenon. So what we try to do instead, since we know the schedule, we try to schedule or post the received before the send. And that means that we try to overlap basically during the computation to also do the synchronization and the send. And we apply this technique for both the static and also the dynamic schedules. Finally, we have the execution engine. So we basically execute the constructed pipeline, and this is compatible with all of the other forms of parallelism already present in Megatron. With this system, we have really adaptable system, so it doesn't matter if we are in the single data center setting or the cross data center setting. We'll always select the best pipeline based on the current conditions. We have extensible systems, so we can configure whether we want to go for the slightly longer optimal schedules or we are okay just with the algorithmic greedy schedules. But also we provide a very nice abstraction to implement any other additional pipeline schedules to the system. And finally, we have a system that's efficient, either using the optimal or near optimal schedules for the current scenario that we are operating in. For the evaluation, we used the single data center system, specifically the ALP system from the Swiss National Supercomputing Center with the following configuration. So we have 4 GH200s per NVLink domain. And what we do here is to basically inject the latency and bandwidth delay directly in PyTorch, so we emulate the cross-data center setup. And this is done for several reasons. The main one is that we really want to be flexible, and we wanted to model different values of the latency and different values of the bandwidth delay. How we specifically do this is to inject spin kernels to PyTorch. So directly on the communication, we basically slow down the transmission or the point-to-point communication. We provide further details in the appendix of our paper. What we pick for this specific evaluation example is a model which is similar to Llama 70B. We span it across 2 data centers with the following parallelism dimensions. On the y-axis, you can see that we will look into iteration time. And on the x-axis, we will basically vary the ratio between the time it takes, the latency time between the data centers and the time of the ratio between the latency time and the time of the forward block. And you can also see the absolute number underneath, such that we have sort of this 2 perspective, how it compares relatively to the time of the forward block, as well as how it compares to the absolute values, which are reasonable for this sort of setups. First, we will look into the static schedules. So we see the 1F1B and the zero bubble schedules, both with the standard implementation in Megatron, but also with this communication orchestration optimization that I showed in the slide before. And we see that we get a significant improvement by posting the receives a little bit earlier, especially for the cases where the latency is higher or the bandwidth is quite low. Now we see the CrossPipe unidirectional optimal schedules and how they compare. And as you can see, it's a significant improvement, especially for the cases with a larger latency or lower delay, or lower bandwidth. We see also the subscheduling, the algorithmic schedule, which are near optimal, so they very much compare to the optimal schedules in this specific scenario. And then we also have the weight pattern of the CrossPipe optimal schedules. We see that in the single data center setting, we are always as good as the state of the art. And in the cross data center setting, we have significant improvement with up to 33.6% training time reduction. While it's an important thing is that while we adhere to the same memory constraints. We also plot in the same plot the prediction of our performance model, and we see here that we follow always the same trend for every one of these settings. In our paper, we performed much more evaluations. We did multiple model evaluations. We varied the number of data centers from 2 to 4. We increased the global batch size. We increased the memory budget. We also activated the activation recompute and see how it affects the performance. We looked into the pipeline parallel versus data parallel trade-offs. And we also mixed the latency and the bandwidth delay, not only studied them separately. So we have many of these results in the full paper. But what I want to say here is that consistently, the performance was the best for our CrossPipe implementation. To summarize, we looked into the cross-data center training, and specifically if the data parallel spanning across the data center boundary is better, or the pipeline parallel is better. And using our performance model, we established that the pipeline parallelism dimension is better across the data center boundary. We introduced 2 schedule algorithms or scheduling creation algorithms. One is the CrossPipe optimal scheduling using the constraint optimization solver. And the second one is the algorithmic greedy schedule construction using the sub-block scheduling approach. We showed how we implement CrossPipe into the Megatron LM and how it sort of composes together with the whole training system. And finally, we showed that CrossPipe consistently outperforms the static schedule. Our code is available open source, and I'm happy to take any questions.